Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with Yi, who's gonna walk us through Axiom. Yi, thanks for taking the time, man.
Yeah, thanks for having me.
Yeah,
Yeah,
pleasure to
excited
have you
to
on,
walk through
dude.
it.
Why don't you briefly introduce yourself, introduce Axiom, and then we can directly jump into the code.
Awesome. Yeah, my name's Yi. I'm one of the co-founders of Axiom. Axiom allows smart contracts on Ethereum to compute over the entire history of Ethereum. And the way that works is that if you want to run a query over the Ethereum history, you can send that to our contract on chain. We'll get the result and generate a zero knowledge proof that the result is correct and authentically accesses the history of Ethereum. We verify that proof on chain and reconcile with the root of trust for all historic Ethereum block hashes. And we send the results and a callback to your contract. So yeah, really excited to walk through how we actually accomplish that on chain today.
Awesome. That sounds really cool. So one example would be, for example, I think in the docs it's if I want to get the average of your ETH balance from the last 20 blocks, this is something you could do with Axiom, right?
Yeah, that's exactly right. So we make every piece of data that's ever appeared on chain available. So that could be your historic balance, it could be historic transaction data or event logs, and we let you mix and match those heterogeneously within a query. So you could have a event log from one block, a balance from another block, or a contract storage variable from another block, all bundled together.
Nice, nice, really cool. Yeah, why don't you walk us through the docs?
Cool. Yeah, so I'll walk through first just what a user flow to actually integrate your contract with Axiom would look like. So we have a starter create Axiom client uh, script. So I'm initializing a new project in my current director. We let you choose between having the queries being submitted from a Next.js front end or a web app or just a Node.js script. So here I'll just choose Next.js. And we let you choose your favorite. So once it finishes installing, what this is going to do is initialize a Foundry project with a smart contract integration into Axiom preloaded, as well as a default Axiom circuit, which will just compute the average balance that was alluded to earlier. So if I open this up in VS Code, then what you'll see is two important components. First, in the app folder, we have an Axiom circuit, which takes in some inputs. In this case, the inputs would be the block number and address that we want to compute the average balance of, and uses our TypeScript SDK to actually constrain the average balance over 8 samples at a spacing of 900 blocks backwards from this block number. So you can see we do some validation, and then we call some special functions like getAccount to get the actual balance of your account at those blocks. So what we're doing here is accumulating the average balance to this total value, and then we find the average by dividing the total by the number of samples. At the end, we specify using this add to callback function the ultimately ZK-proven results that you want Axiom to send to your smart contract in a callback.
Okay. Okay, really cool. So basically, okay, this is basically a circuit. What is it using in the background, like technology wise for the ZK stuff?
Yeah. So this is all using our TypeScript SDK. So it's through this Axiom Crypto / client library. It's TypeScript bindings for our Rust ZK circuit library, which is built on top of Halo 2. So Halo 2 is a ZK proving framework that's being used by Zcash and the Ethereum Foundation for the ZK EVM.
Nice.
So it's typically actually pretty hard to use, but in order to make it more accessible for developers, we made it so you can use Halo 2 using just TypeScript. And so we feel like this is a much more friendly interface for people to actually interface with circuits.
It definitely is. If anyone has ever used it directly, they know what I'm talking about. Yeah, this looks really usable.
Yeah, so The second piece that is important when writing an integration into Axiom is your smart contract. So we created an abstract base class, this Axiom v2 client base. And the important thing in your contract is that you need to implement the piece where Axiom will send you a callback of ZK verified results. So to do that, you need to override two functions. One is validate Axiom v2 call, and the second is Axiom v2 callback. As the name suggests, the first one validates that a callback sent to you by Axiom actually pertains to your contract. So we provide quite a bit of information that you could validate, but most commonly contracts will want to validate that the source chain is actually what you expect. And second, that a special piece of information called the query schema associated to your circuit actually matches what you expect. So the query schema encapsulates the information of what your query is about, but not the specific inputs that were sent to your query. So in this case, the query schema would be a hash that encodes that you're asking for an output of this average balance circuit. So this is necessary just to filter out cases where someone malicious might send a callback to your contract that doesn't actually pertain to it. Now, the second thing is the Axiom v2 callback function, which actually pertains to your business logic from the outcome of the query. So here we provide the results in this Axiom results array, and you can parse that array into the format that you anticipate. So in this case, we added the block number, address, and actual average to the callback in the circuit. And in the solidity function, we parse that into the types that we actually expect. So in this example, we just simply store the proven average balances in a mapping. But of course, you can use this for whatever you would like in your downstream application.
Nice. Yeah, this is okay. Maybe the callback functionality. Okay, so this contract inherits from the if you can scroll to the top again, it inherits from okay, v2 client. Okay, and the v2 client calls into that and calls the callback.
Yeah. And so v2 client has some permissioning to only allow the Axiom v2 query contract to actually invoke the callback. So the flow is that the ZK verification is done on-chain in our query contract, and then it forwards these callbacks to the individual client contracts.
Okay.
So we've provided some Foundry extensions to actually test these to the circuit and the contract against each other. So if I do forge test, we have, okay, I specifically tried to prevent this, but you need to set a environment variable. And well, it's maybe hard to do this on stream. Hopefully this works. Great. So, okay, supposing you successfully set your .env, what we've set up some extensions to the Foundry test framework to allow you to test your callback and to test sending your query in a Foundry native way. So let me walk through how that works. So first, we can take a look at the actual test file. So here what's going on is we created an extension to the Foundry test framework called Axiom test. You can use this as a drop-in replacement for Foundry test. It provides just an additional set of cheat codes which pertain only to Axiom. So the first is that in your setup, because Axiom is reading from historic on-chain data, it really only makes sense to test on a fork. So here in the setup, we specify that we're testing on Sepolia and that we fork at this specific block. The second thing is we need to specify which circuit we are interacting with. So here we specify that we're compiling this circuit and we want to use some inputs which we specify in a JSON. We provide this contract Axiom VM, which is intended to mimic the Foundry VM. Once we compile, we can get the query schema, which was the unique identifier of the circuit that we alluded to earlier. And we instantiate this average balance contract using this query scheme. Now, we've provided two important cheat codes to enable testing. The first, which is Axiom VM.send query args. This prepares the arguments to allow you to send a query to Axiom on-chain. So there are quite a few arguments, including the source chain ID, an encoding of your query, and some other data specifying your callback, what sort of fees you want to send, what address gets a refund, and so on. So these are all configurable, but this overall cheat code just gives you sensible defaults for all of these. And second, we provide a way to prank the callback into Axiom. So to give some context on why that is necessary, in our overall architecture, the developer will run a circuit, send a query on-chain to Axiom to request authentication of all the data inputs to that circuit, and then we will fulfill on-chain with a ZK proof. So the callback the developer receives is actually triggered by Axiom. And so to test your integration, the crucial thing to test is that the callback that your circuit is creating is actually compatible with what you expect in your smart contract. So what this prank callback function does is exactly mimic running your circuit, getting the data inputs authenticated on-chain, and then sending the callback to your callback in your client circuit. So basically, these two cheat codes allow you to test your Axiom circuit in a similar way to testing a standard smart contract integration.
Okay, could you maybe go back to the diagram and explain that one more time, because I think that's super important to understand the integration flow.
Yeah, so the flow is you're trying to write a contract that integrates into Axiom, and so you want to do some computation over some historic data on Ethereum. So you express that in what we call a client circuit. So that's a TypeScript file that implements a function kind of like this. Now, what this circuit will do is some computation over some historic data. So in this case, the historic data is the account balances, and the computation is the averaging. Now, we separate the verification of the average balance computation into the verification of the computation, which is actually being done in a client-side ZK prover, either on your web app or on your server via Node.js. Once that compute proof is done, we package that into a query which is sent to our on-chain contract. So that's what this send query function is going to do. So we index that query and generate a ZK proof of the authenticity of all of the historic data inputs. Once that's done, we send that proof on-chain to our Axiom v2 query contract, where it's verified and triggers the callback. So the interaction points that a developer would have with our contract are sending the query and then receiving the callback.
Okay. Okay, that makes sense. Also interesting, so you guys pay the fees basically at the last step where you post on chain to trigger the callback.
Yeah, that's right. So we require developers to escrow some fees in the send query step to cover the proof verification and the callback. And we allow developers to configure sort of what their desired gas is.
Okay, I see. How long does this take?
Yeah, it depends a bit on how large your query is. So it's generally on the order of minutes. Currently on mainnet, we support up to 128 data accesses. So what that means is a data access is 32 bytes of data from any piece of Ethereum history. For up to 8, it's about 2 to 3 minutes. For up to 32, it's about 6 to 7 minutes. And then for 128, it takes a bit longer, around 15 minutes.
Okay.
So to write an integration to Axiom, you have to write the circuit and the contract that integrates the callback that's taken from the circuit. And we provide these Foundry tools for you to actually test this integration using these cheat codes. Yeah, so maybe we can change gears and talk through what actually enables all this to work.
Let's do this.
Cool. So I'm going to switch away from my client's repo to the actual contracts repo. So here, let me see. There are sort of two pieces to our application. So the first is that we need to actually create a root of trust on-chain to verify the queries against. What that means is that when you make a statement about historic on-chain data, it's not really an absolute statement, since ultimately every user might have a subjective view on the history of Ethereum. But what makes it objective is that we're going to verify the ZK proofs on-chain relative to the access to block hashes that the EVM actually has through the block hash opcode. Now, you guys probably know that the EVM can only access the last 256 block hashes natively.
Yeah.
And so what we need to do is to make the rest of the block hashes back to Genesis actually accessible to our contract to verify against. And so the way we're going to do this is using a Merkle mountain range data structure. And we do this in our contract Axiom v2 core.
Okay, Merkle mountain range. Okay, you have to explain what that is.
Yes. So Merkle mountain range is a data structure which is a sequence of Merkle trees. So there's some peaks of the trees, and they're descending. And the idea is that if you have a variable length array of hashes, then you can construct a Merkle mountain range by first taking the largest Merkle tree, which will fit in the prefix of this array, and constructing the Merkle root of that, and then repeating. So let's say I have an array of length 13, then the biggest Merkle tree that I could fit would be first of length 8, then that would leave 5 more hashes. Then I would take a Merkle tree of length 4, that would leave 1 last hash, and then that would leave just the Merkle root of that single hash, which is itself. And so the Merkle mountain range that encodes this length 13 array would be a Merkle root of size 8, a Merkle root of a tree of size 4, and a Merkle root of a tree of size 1. And so in general, if I have a list of hashes, which is variable length, then let's say there's n hashes, then the Merkle mountain range will be a list of Merkle roots, usually of size log n, which together commit to the entire history of all of the hashes. Now, we represent this Merkle mountain range as a sequence of the peaks that I just mentioned. And so in this bytes 32 array, the ith element always represents either 0 or a Merkle root of 2 to the I hashes. And then we keep a convenience variable peaks length just to remember how many of these peaks actually are filled in, since quite often many of them are 0. So the reason that this data structure is helpful is that it allows us to commit to the entire history of Ethereum block hashes while only using logarithmically many hashes. So in this case, we choose a maximum of 32, just because that would be over 1 billion blocks.
Okay. Yeah, it's funny when you said you need, which makes sense. You need all the hashes from every block in Ethereum history. I was gonna ask, okay, this must have been very expensive to set up, but yeah, makes sense to have some efficient data structure that does it for you.
Yeah. So we have to do 2 things with this data structure. And the first is that we need to set it up. And the second is that we need to keep it updated. So let me talk through sort of how we do that. So the first thing to know is that we actually, for cost reasons, don't use a vanilla Merkle mountain range. We actually use something called a padded Merkle mountain range. So what is a padded Merkle mountain range? So I told you that a Merkle mountain range is a sequence of peaks, which are roots of Merkle trees of decreasing size. And if you imagine that we're creating this Merkle mountain range over all the block hashes, well, new block hashes are appended to the end of the array, and we need to update our mountain range. And so what that means is the last few peaks actually tend to change quite a bit. Since, if I have a peak of height 1 and I append just a single block hash, then I need to change that. And so if we were to just update all those peaks all the time, we would be using a ton of S stores. So instead, what we do is we keep a padded Merkle mountain range, which consists of a Merkle mountain range over a Merkle mountain range with only Merkle roots of depth at least 10. So we basically group the block hashes into groups of 1024 and create a Merkle mountain range over Merkle roots of groups of size 1024. And so what we're left with is a suffix of the array of historic block hashes. And we form a complete Merkle root over that suffix. What I mean by that is we zero pad it to 1024 hashes, and we compute the Merkle root of those hashes. And so for us, a padded Merkle mountain range is a Merkle mountain range over the Merkle roots of groups of 1024 block hashes, and then this final padded leaf, which encodes up to 1023 block hashes at the end. Now, of course, that still commits to the entire history of block hashes, just because this complete leaves Merkle mountain range commits to block hashes up to the last multiple of 1024. And this padded leaf commits to all of the recent up to 1023 block hashes. And this is the data structure that we keep updated in our smart contract. Okay, so we keep this in this block hash PMMR data structure. So for us, PMMR refers to padded Merkle mountain range. And we also keep snapshots of this PMMR indexed by the size of the range of block hashes that they commit to. So in PMMR snapshots, either the value is 0 if there's nothing stored, or we have a hash of the padded Merkle mountain range, which commits to the blocks between 0 and PMMR size. So our goal in this Axiom v2 core contract is to keep this block hash PMMR and PMMR snapshots variables up to date as new block hashes are appended to Ethereum. So there's sort of two pieces to this. The first is once we deploy the contract, like how do we actually get it in sync in the beginning? And then second, once the contract is live, how do we keep it in sync? Now, the first thing to do is once we deploy the contract, we need to run this update historical function. What this does is starts from a validated block hash and proves a chunk of 128 times 1024 block hashes backwards. So the way we're going to prove any block hashes at all is to verify in ZK that the header of the previous block lies in the present block, the header of the present block lies in the next block, and so on. So if we can prove that, then we would establish the validity of the block hash of the previous block contingent on the validity of the block hash of the present block. And so what we're going to do is verify ZK proofs to that extent, and then extract data that's necessary for us to actually populate these Merkle mountain ranges. So just to talk through how we do that, we're going to store for each group of 1024 block hashes, something we call the historical root. So the goal here is for this mapping to map the starting block number to a Keccak 256 hash of the previous hash, the Merkle root of the hashes in that 1024 block chunk, and then a variable which is num final. Num final is either 1024 if we have all of them, or the length of the prefix of the block hashes we have if we only have some of them. So in this way, we have a commitment to the previous hash of each block in a 1024 block chunk, the Merkle root over those block hashes, and the number of block hashes in that chunk that we actually have already proven on-chain. And what we're going to do is populate this historical roots mapping and then use it to generate the Merkle mountain range and the snapshots of the Merkle mountain range. Okay, so in the bootstrapping phase, what we do is we call update historical to move backwards. So this function takes in a zero knowledge proof, which is in this proof data. And first, we'll parse a bunch of information from the proof data. So in this, whenever you use a zero knowledge proof on chain, there are some public inputs and outputs of the proof, which one has to read. So in this case, what we're reading is the claimed previous hash of the block before the chunk of blocks this proof refers to, the claimed last hash, which is the last block hash in the string of blocks this proof refers to, the starting block number in the chunk, the ending block number in the chunk, and finally, the Merkle root over all of the block hashes in this chunk. So this is all the data that this zero knowledge proof is attesting to. And this proof would show that there exists a sequence of block headers of length 128 times 1024, such that the previous hash is this, the last hash is this, the starting block number is this, the ending block number is this, and then the Merkle root over all the block hashes is aggregate hash. We do quite a bit of validation to check that this is actually the format we're expecting. So we check that we are at a multiple of 1024 for the starting block. The number of blocks that is claimed is what we expect. That the end hash that we're actually looking for connects to the string of historical roots we've already proved. So basically, we're proving something about a string of block headers. And to make sure that it actually has something to do with what we're checking on chain, we need to check that we've already authenticated the end hash either through the block hash opcode call or through a zero knowledge proof. And so this check makes sure that we've already committed to this end hash in this historical roots mapping. Okay, so all of these make sure that what we are proving in this ZKP actually has something to do with the block hashes on Ethereum. Now we actually need to extract information from these public inputs and outputs of the ZKP. So what we're going to do is actually deposit 128 Merkle roots of chunks of size 1024 on chain due to this proof. And so we first check that those are actually valid by checking that their Merkle root is equal to this Merkle root of the full 128 times 1024 block hashes. We check that, and we also check that this ZKP actually verifies on-chain. So once we've passed all these validation steps, what we've validated is that we have a zero knowledge proof that establishes there is a string of block headers between start block number and end block number that have a previous hash and end hash as claimed, and whose aggregate Merkle root is actually equal to the Merkle root of these individual 1024 block chunk Merkle roots. So that's definitely a mouthful of data that was validated. And now we're going to actually put it into the data structures that we care about. So here, what we do is that we're supposed to fill in this historical roots data structure. And if you remember, the historical roots at a block number is supposed to be equal to the hash of the end hash, of the previous hash for that block number, the Merkle root over that chunk, and then the number of final elements in that Merkle root. So we're going to exactly fill that in. So we already have the Merkle root that's in this roots array. We also already have the previous hash that's simply extracted. Okay, so what's missing is basically this previous hash. So what we're going to do is actually provide these previous hashes in some arguments to this function and check using Merkle proofs that they are committed to in the Merkle roots that we're giving. So it's a little bit complicated, the logic, but here what we're doing is just checking that the end hashes that we're going to provide as the previous hashes in this historical roots are actually committed to in these roots that we've already validated. And so once we do that check, we can fill in our historical roots mapping with a commitment to the previous hash at each root, the actual root, and the fact that these roots were size 1024. So once we've done this, we've backfilled our mapping by 128 Merkle roots of 1024 consecutive block hashes. So yeah, when we first deploy the contract, we actually call this a little over 100 times to go from the current block all the way back to Genesis. And the outcome of that is that we filled in our historical roots data structure with every 1024 blocks holding a commitment to the Merkle root of those blocks, and then some other data necessary to validate that chain of proofs back. And so here we've constructed a root of trust, which commits to the entire history of block hashes of Ethereum, all verified in ZK.
That's really cool, dude. That's really cool. Okay, why 1024? Just arbitrary number?
Yeah, 1024 is chosen for two considerations. The first is that we need to keep this updated. And so as blocks are appended, we need to prove the new suffix of the block hashes of Ethereum that aren't covered. And so to do that, we need to, we chose a chunk size with which we append blocks. And so we want that to be relatively smaller so that the proving time for appending is cheap. But also we don't want it to be too small because otherwise we're updating just all the time.
Okay, so the Axiom system always lags 1024 blocks behind.
So it does not lag 1024 blocks.
Okay.
We designed the system so we're able to prove fewer than 1024 blocks. So that's the purpose of this num final number. We can prove up to 1024 blocks.
Okay.
So somehow the cost of generating the proof depends on the max number of blocks, but we are able to prove fewer. And so we maintain the invariant that the Merkle mountain range that's constructed over the historical roots, Merkle roots, always commits to everything that is not accessible natively in the EVM. So always commits to at least everything that is older than 256 blocks.
Okay.
And yeah, so maybe I can talk through how we actually update.
Yeah.
Yeah, so let's suppose we did this update historical, it's this kind of whole procedure, but now everything's in sync. So some new blocks happen, and what we're going to do is call update recent. And this is another function that takes a ZKP. And what it does is it extracts information about the previous hash, the end hash, start block number, end block number, and root. So let me tell you what these mean. So this proof data is a claim about a string of 1024 block hashes. Up to 1024 block hashes. The previous hash is the claimed block hash before that string starts. And the end hash is the claimed hash at the end of that string. And finally, the start and end block number are where the string of block hashes starts and ends. And finally, the root is the Merkle root of the zero-padded Merkle tree of size 1024 with those block hashes. And so the idea is that we allow ourselves to replace the suffix of our padded Merkle mountain range with the Merkle root that is provided here. And thereby extending the set of block hashes that we're actually committing to in our contracts. So just to walk through kind of briefly, since it's pretty similar to the previous case, we do a lot of validation just to make sure that we're proving at most 1024 blocks, that the end block is actually within the last 256 blocks that the EVM has access to. And finally, that the end hash actually matches what we get from the block hash opcode. So here we're actually rooting our trust in the EVM's native access to block hashes. So once, and then of course we validate the actual ZK proof. So once all these checks pass, we know this output data is authentic, and now we're ready to update our data structure. And here it's a little bit complicated. So basically, we have this root, which is a Merkle root of a zero padded Merkle tree. And so what we can do is that if the Merkle root is how to say? Depending on what's in this Merkle root, we can update our Merkle mountain range accordingly. So basically, if the Merkle root actually is a full Merkle root of 1024 blocks, then it means that in our padded Merkle mountain range, we need to update these complete leaves, which remember was the Merkle mountain range over complete Merkle roots of 1024 blocks in a row. On the other hand, if the root is still a zero padded Merkle root with non-trivial zero padding, then it means we just need to update this padded leaf. So the rest of this function just implements that logic to actually update our Merkle mountain range. And so once we do that, we update the historical roots with the roots that we just received. And we also update the block hash PMMR and the snapshot of the block hash PMMR. And so whenever we prove anything in Axiom, we prove it relative to these snapshots, and which are commitments to this padded Merkle mountain range of the block hashes. Okay, so just to sort of summarize what the goal of this Axiom B2 core contract is, we have these three data structures: the historical roots, which stores raw Merkle roots of chunks of up to 1024 consecutive block hashes, which have been verified using ZK to lie in the history of Ethereum. On top of that, we build a padded Merkle mountain range, which is maintained to commit to the entire history of Ethereum. And we take snapshots of that in this PMMR snapshots data structure. And so when we generate a proof for a query into Axiom, the key thing we're going to reference is actually this PMMR snapshot status structure. Okay, so let me move on to how the query system actually works.
Yep.
Okay, so let me open this. Okay, so the interface that users are going to interact with to actually send queries, get callbacks, and do transaction state management is called Axiom v2. So users can send queries to us on-chain and receive results on-chain. So let me first talk through how users actually can interact with the system. So there's quite a bit of configuration, but the most important function for the end user is send query. So this allows users to specify that they would like to query over the entire history of Ethereum. And the inputs here are the source chain ID. So this is obviously the chain that the user wants to reference information from. Currently, we're deployed only to read Ethereum mainnet from Ethereum mainnet, but in the future, we'll support different cross-chain reads. The second, there's some information pertaining to the data query and the compute query. So for us, we split up the query into two pieces. The first is the on-chain data that a user would like to access. And the second is the computation that the user would like to do over that on-chain data. So the circuit that I showed in the beginning of the episode is essentially a TypeScript specification of the compute query. And the data query is derived from the data accesses that that circuit makes. Finally, the user can specify some callback information about what contract they would like the results delivered to, and some fee information about the sort of gas limits that they would like to send with their query. Finally, we offer refunds if, for whatever reason, the query is not fulfilled, and we have a user salt that allows the user to tag their query with a unique ID. And the last argument is some bytes for the user to provide data availability for the data query. In order to verify the query, we actually only need this hash encoding of the data query. But in order for an off-chain prover to know what the query actually referenced, we need data availability for the query in some way. So we offer the option for you to provide that data availability on-chain right now. In the future, we're going to offer data availability through IPFS or through an API call. So let me just talk through what these other arguments to send query are. So these will all be just sort of auto-generated by our SDK from the circuit. So first, the compute query stores a bunch of metadata that are associated to your circuit. So this includes some information about the degree, which is the size of the circuit, the number of public outputs, which should be sent to the callback, and then the verification key and the actual proof that's being generated on the client side. Second, the callback gives information about the target address, and then, so that's the address of your contract, and then some extra data, which we're going to pass at the end of call data through the callback. And finally, in the fee data, we allow you to specify what max fee you would like us to send the verification and callback with, and also the gas limit to allocate to your callback. So we require you to escrow a fee while sending the query in accordance to these two parameters. And finally, we charge a query fee, which is 0.003 ETH, and we allow users to override it if they would like to give a higher fee. This would be used if users want to send queries which lie outside of our usual range and pay more for it. Okay, so in the process of using Axiom, a user would send this query through either a web front end or a developer's smart contract. And so that query gets indexed in our contract sorry, let me just show the place, in this queries mapping. So we always store the metadata for the query indexed by something we call the query ID. So that's simply a commitment to all of the relevant data to the query. So you can see we computed here. It includes a hash of the query itself, and then also a commitment to all of the relevant on-chain information. So in this case, the target of the callback, the extra data, the salt the user provided, a refund address, and also the caller address. So when the query is sent, all we're doing is computing this query ID, escrowing funds via this send query function, and then emitting an event to record that. And so just to show how the funds are being escrowed, we do some validation checks to make sure that the query is not duplicated, that the user is sending a valid max fee for gas parameter, and then we compute the price of the query. So that price is simply what it would take to pay for the callback with this max fee, and also for the proof verification. So at the moment, the proof verification is 420,000 gas. So we pass through the gas to the end user and also add a Axiom query fee of 0.003 ETH on top. So we have some logic just to reconcile the user balances with this fee. And if everything passes, then we set up a new query in our system, which is active, must be fulfilled by some deadline, has the relevant gas limit, and we have a payment. And so there's no payee yet for this query because the address that fulfills will be entitled to collect the payment. So far we've sent a query and we're able to it's now eligible for on-chain fulfillment. So the second half of the protocol, which is important, is the ability to actually fulfill. So let's talk through how that works. So that goes through the fulfill query call. So you can see in the arguments that it divides into essentially two pieces. The first three arguments are the ZK proof, which verifies the results of the user's query, and then some witness data, which allows us to reconcile that proof against Axiom v2 core and the actual results. And finally, we have some data pertaining to the callback and the query that are essentially here for gas optimization purposes. We're storing mostly commitments to the user's data, and then we provide them as witnesses and some of the function arguments to save gas. Okay, so the first thing we need to do is actually to verify that these compute results are accurate and that the proof attests to them. So we do this in this verify results function. So there's a couple steps here. The first is that we're going to read all of the relevant data from the proof itself. So our proof is a statement that for data from this source chain ID, we got a hash of the compute results. And those results are for a query with this given query hash, this given query schema, and they're proven relative to this hash, which we call the block hash MMR Ketchak. So that is a Ketchak hash of a claimed Merkle mountain range of block hashes, which all of these proofs are relative to. So this proof says, if you accept that this is a valid commitment to a Merkle mountain range of block hashes, then you should accept that the results of this query are given by this compute results hash. And finally, we have some metadata of the payee, which is the prover who should get paid for this query, and the aggregate vkey hash, which is a commitment to the ZK proof structure, which was shown in this query. So we've extracted all this data from the query, and then we're going to verify it on-chain. So there's sort of two types of verification. The first is we need to check that this Merkle mountain range of block hashes is actually present in the history of Ethereum. Obviously, if I prove relative to a fictional Merkle mountain range of block hashes, it doesn't really matter what my ZK proof says. So to do this, we call out to an Axiom v2 header verifier contract that we've implemented to abstract away this check. So we provide that the claimed Merkle mountain range of block hashes, as well as some witness data, which helps us reconcile against our on-chain cache. The reason we've designed this to abstract away this verification is that it allows us to do this here on L1 against our core contract, and also in the future on L2 against a commitment to the history of L1 that is message passed. So once that check passes, we know that the Merkle mountain range we're proving relative to is actually authentic. And so what's left is to check that the ZK proof is correct, and then also that the relevant metadata of the ZK proof is correct. So here we need to check first that the claimed results are actually equal to the results in the proof. So that just checks that we actually got the correct claim. And finally, we check the permissions on the prover. So we are permissioning the set of allowed provers in our initial deployment. This is mostly for security purposes. And finally, we check that the aggregate vkey hash, which is a unique identifier of our ZK circuit, is allowed. So here we have a mapping of allowed aggregate vkey hashes. And we're also able to allow new aggregate vkey hashes on a per query basis. So once all these checks pass, we're able to actually verify the ZK proof itself. And if that passes, then the entire verification has gone through. And we've shown that these compute results actually are the results of the Axiom query relative to a validated Merkle mountain range of block hashes, which we've checked on-chain. Okay, so once we've fulfilled all these things, or once we've verified all these things, we know that the query result is actually correct. And what we're going to do is now process the transaction state. So for that, we need to figure out the query ID and make sure that these the callback we're providing and all the other query metadata actually corresponds to what we had on chain. So we check that the query hash matches, the callback is actually what we expect, and that the query is in the correct state. If all of these pass, then we can set the payee to be the payee set in the proof. So that is the prover who should get paid for fulfilling. And we set the query to be fulfilled. And finally, we send the callback to the user's contract. So here we construct the callback, and we always constrain that the callback is to an Axiom v2 callback function, and we fill in each of the fields that we promised the user. And finally, the last thing that might be a little bit interesting is that when we actually send the callback, we need to check that we have sufficient gas to forward on to the call. So we ensure that we're respecting the callback gas limit, and then if we don't have enough gas left, we'll revert. And we call using this custom call with no return function, which uses assembly to adapt from excessively safe call. So that's sort of the full flow for Axiom v2 query. First, we start from a user sending an on-chain query. Then we generate a proof, validate it on-chain, and fulfill and send a callback.
Okay. Awesome. I think we're at 55 minutes. Maybe a good time to stop here? What do you think?
Yeah, I feel like there's a bunch more stuff, but it's pretty technical. So this might be a good. Uh,
We can definitely do a part two sometime in the future if you like. But I think for this one,
yeah,
uh,
I think
this
that's all
was a
good.
lot. This was a lot. But really, really interesting. So thank you for taking the time and for the great presentation. I'm gonna put the link to the GitHub in the description down below. Um, the Axiom Twitter, the docs. Anything else that would be helpful?
I think that about covers it. So yeah, we just launched on mainnet last week, and watch out for some new releases from us in the coming weeks.
Awesome. Yeah, that's a very, very, very interesting use case. I'm excited to see what people are gonna build on top of this. Historical data, this enables a ton of new applications. So great protocol, and again, thanks for taking the time.
Awesome. Thanks so much for having me. Really enjoyed
Awesome.
it.
Thank you. Bye bye, guys. See you in the next one.